All right. How's the sound for everyone? I guess let me know if there are any technical issues. Hopefully you can hear me. And when I start sharing the screen that you can see all of that. Okay. So, what we're going to be doing today, sorry, I have another screen here that I'm looking at that has some of the other things I'm getting ready. So what we're going to be doing today is this pre-calculus review that I posted. The problems went up this weekend. The solutions were posted this morning. Hopefully you had some time to at least look at the problems and get an idea of which ones you were most interested in seeing how they get worked out. So let me share this. Okay. So on our Canvas page, we have the pre-calculus review and the solutions here. If you actually take a look at the solutions, and I'll just, for all the quizzes that are going to be happening in labs, there will also be solutions posted for those. And how I try to do these solutions is I don't want to just write the answer. I try and show the work as well as a little bit of a description of what's going on. So not only can you see the answer you're supposed to get, but also it's a kind of written down version of what I would say if I was going to try to explain this problem. Um, some of this I didn't do all of it. The graphing problems we can graph those on a graphing calculator. So I left those blank, but everything else I showed the work here. And some of the bigger problems, like some of these, there we go, inequalities, this solution is somewhat substantial. Now these solutions in here, this is a written explanation of what's happening. This is way more work than you would need to show. If you were working this out, I guess Yeah, you wouldn't need all the words explaining why you're doing what you're doing necessarily. You would just kind of do it. And the fact that you're doing it lets me know, okay, you know the right steps, and that's what I'm really looking for. So, what I guess I want to start with is, are there any of these types of problems that anyone is especially interested in seeing? I can pick a couple that seem hard, but if any of you have problems that you'd really like, that'll make sure that I'm getting some that you, at least some of you, find helpful. Thoughts? Okay. Well, let me pick a couple of these. If you have questions, make sure you let me know. Either chime in with a microphone, or we have there's a chat feature that I'll be keeping track of, and I'll look for questions there. Let me. Okay. So 12 to 15. Okay. So the graphing ones. Right. So before I really get into this a lot, I'll say that, well, in this isn't in the Ranger, but in 11, by sketch the graph without a graphing calculator, a lot of this is know kind of the general shape. Um, it wouldn't have to be the most precise thing, but for example, x squared, if I draw a little picture, x squared I know is a parabola and looks something like this. Now, especially here, because I'm trying to do this on my mouse, the picture isn't great. It's supposed to be symmetric, so there could certainly be better drawings, but the kind of basic features you know. So it starts at the origin and then goes up, kind of curved in both directions. So that's a sort of basic understanding of this question 11. They don't have to be perfect, but knowing really key features. As another example, say 1 over x here, you don't have to have this perfect, but knowing that it has something like this. There's an asymptote here, and then it has a horizontal asymptote as you go out to the left and right. And again, exactly which points it has, I'm not going to be worrying about too much, but being able to kind of quickly recall these basic sketches will help us, because it'll be good to have a picture in mind when we're doing some algebra, asking some kind of algebraic questions. Okay. For number 12, what is, so the topic that's encountered in precalculus, and I guess a disclaimer I should say is not, precalculus is kind of a broad topic, and so it can happen that in whatever your precalculus class was, some topics were emphasized, some might not have really been there at all. And so sometimes graphing isn't emphasized, and that's a choice that teachers can make. But the idea is that in these cases, what has happened is you're taking a basic, sometimes called parent function, and you're moving it around. So for x minus 1 squared, if you're looking at this, so actually all of these, there are these extra numbers in here, but there's a basic function here. This one is x squared, then x to the fifth, the square root, and so on. There's a basic function, and that's going to be the main shape. So in this case, how I would go about understanding this is you first look at this and say, okay, this is x squared. So I have this shape that I'm going to be tracking. But then a general rule for these graphs is if you take what's inside, or if you add or subtract inside the function, so inside meaning the minus 1 is, so you have x minus 1 and that thing is being squared, compared to outside, in this case, the second example, you have x to the fifth, and then you take that fifth power and add 3 to it. If you're inside, that is moving your graph left and right. And in this case, it's a little backwards, where subtracting often, if you're thinking about a number line, it means you're moving something left. In translation this way, it corresponds to moving it right. So this graph here is exactly the same shape, but instead of being based at 0 here, you're moving everything right, and so it's still the same shape, just your kind of center point is at 1, but then you still have the parabola shape, so you're going up like this. And so that's what these problems are saying. Each of them, there's a basic shape, which you can also get from, if you did the previous problem, that's what the basic shape is. But all of these extra numbers correspond to taking that shape and moving it around. Or in one case, multiplying by 2 says it's steeper by a factor of 2. So in this case, the absolute value function has this V shape. So here the lines are supposed to be straight as opposed to curve for the parabola. And here you'd maybe keep track of this by saying this point for input 1, the output is 1. The stretched version has the same V shape, but at 1, instead of being at height 1, it's up at height 2. And pretend this is straight. So it's this same shape, but it's steeper. And that's what this extra factor of 2 does. So that's this kind of problem. And I'll say this isn't the most important skill, but having an idea of saying, of looking at these functions and say, there's a basic shape and I've kind of moved it around. That can give you having that level of understanding can help when it comes time to asking questions about these kinds of functions. Questions about any of these? If you're not sure, I would say go ahead and, so let me actually do this. Oops, I don't want these pictures anymore. Okay. So one thing that you can do, pick, all right, let's take this one, e to the x plus 2, and then plus 1 outside. So the idea is you start with e to the x. That's this basic shape. And these extra things move it around. So for instance, e to the x plus 2, oops. And sometimes in here, we might need to put it in parentheses just to make sure that it's grouped correctly. So here, this plus 2, what it does is it takes that basic shape and moves everything left by 2. And then the last part, where there was also e to the x plus 2, and then plus 1. So this one takes e to the x plus 2 and then moves everything up by 1. So that's how those problems are supposed to go. Let's see. For 13, talking about the domain, what is important to remember is there are essentially, there are 3 big ways that a function can't be defined. And those are, you can't divide by 0, you can't take the negative of a square root, and you can't put a negative inside a logarithm. So for instance, this first example, you know that if you pick an x like -2, you're going to end up trying to take the square root of -1, and that's not defined. You might say, well, you've seen the square root of -1 before. That shows up in the context of complex numbers, which can appear in precalculus. We're not doing anything with that. No i's, no square root of negatives, those just aren't defined. So we can put in things like -2, but if we want to say which numbers we can put in, what we have to translate is, we know we can't put negatives in a square root. So if this is going to make sense, then the thing inside the square root has to be greater than or equal to 0. And then we can solve this inequality, adding -1 to both sides, so x is greater than or equal to -1. And this -6 out here just doesn't have anything to do with the domain. That impacts what function it actually is, but as far as what x's are you allowed to use as inputs, it just doesn't matter. And we can also see this graphically. If I do this. So the square root of x is this basic shape. We were interested in the square root of x plus 1. If you're graphing this, if you're trying this out and you're looking for some symbols, there's this little keyboard here that has some basic symbols, but also this button functions has the trig functions, logarithms, different roots. Where are you? Those are things that stats things we don't really want. But here x plus 1 shifts it over by 1. And so here we can actually see that answer we arrived at. We only have a graph to the right of -1. Only for things for the right of -1 is there some y value. Is there some point on the graph corresponding to that x value? To the left of -1, there just isn't a function at all. And then that -6 out there just says, kind of like the transformation problem, we shift the whole thing down, which changes the function, but doesn't affect which x's we're allowed to put in. In this third one, what you're doing is you're setting the bottom equal to 0 because you can't divide by 0. So you look for those points. And once you find them, you say, those are the bad points. I don't want to talk about those, aren't allowed. And the middle one is a polynomial. Polynomials are powers of x with constants added or subtracted together. And here, we really avoid any issues. We aren't going to divide by 0. We don't have any roots to worry about. You can pick any x, and you're going to get some number. You'll be able to compute whatever this is if you pick any x. So that means that for this function, and for any polynomial at all, those are always defined. You can pick any x, any real number x, and put that into the function and get something out. So I can talk a little bit more about those, especially this last one, which has some things to do, but I kind of went over it quickly. Okay. So the next group of problem, and this is Anna asked this. I can do one of 14 or 15, but I also want to make sure that other people have questions. So if anyone has a problem they really want to make sure we talk about, I can jump to that, but I can also do one of 14 or 15. And is there a preference for these two? They're kind of the same in that look at the graph and use it to answer questions, but they're very different looking graphs. So let me do number 15 then. And hopefully going through this gives you a feel for what the kinds of questions are. And that'll help when it comes time to looking at the other. So x plus 4 over x minus 1. This. 4 little parentheses to make sure we can divide x minus 1. Okay. So this graph is definitely not one I would expect you to come up with. It's not a really complicated function. Like it doesn't have any powers, but the division makes it so it's not just one that you would know off the top of your head. So this kind of question really needs me to give you the graph or tell you to look at the graph, and then we can ask some questions about it. At least until later in the course, what we'll be doing, that's kind of a few chapters in, is we'll be answering the type of questions that this problem has without using the graph. But we'll have to build up some time to get there. Let me... So let me position things to try to get everything on here. Okay. So in here, the things we want are the domain, horizontal and vertical asymptotes, the range, any zeros, the y-intercept, where it's positive and negative, and where it's increasing and decreasing. So a lot of these words, especially the domain, the zeros, or the y-intercept, those are some that you might also want to find algebraically. As in, I can ask you to find those without the graph, but some of these are ones where, at least for right now, we really do need the graph. So the domain here, this is which x's can we put into this function and get something out. On the graph, what that corresponds to is which x's, so along this axis here, which points have a point on the graph corresponding to them. So 5 right here, you can go up and hit the graph. So that points 5 is in the domain. -1, you can go down and hit the graph. So -1 is in the domain. So you're looking for any x's which you can't find a point on the graph with that x. And what can maybe help some is this circle hung out here. What we can see, jumping ahead to the next problem, there's this vertical asymptote here where as we get as we move in towards 1 right here, put this here. As we get closer to this line, we keep going up and up and up. And if we keep coming this way, we keep going down and down and down. But there's no point on the graph that actually corresponds or that actually has an x coordinate of 1. So that's the point that we're looking for. So the domain is everything except 1, and we write this in interval notation. So interval notation is, say, how we read this is we're beginning at -infinity, which means we go all the way down through the negative numbers. We go up to 1. We don't want to include 1, so we skip over it. This little cup union symbol says there are 2 parts to this. There's the part to the left of 1, and then we skip over 1 and then go all the way up to the right of 1. This answer also makes sense if you look at the equation here, because what is a domain problem? Well, with a fraction, one big thing you need to look for is you can't divide by 0. And if you say, where might the bottom be 0? Well, if x minus 1 equals 0, that's the equation you set up to try to answer that question. That gives you exactly x equals 1. So that's the point that we don't want to include. In figuring out the domain, we essentially also came to the conclusion that 1 is a horizontal asymptote. Sorry, not a horizontal, a vertical asymptote. Sorry, there's a deer outside my window and it's distracting. So there's a vertical asymptote at 1, but we also want to look for a horizontal asymptote. So this vertical asymptote is this line where we keep getting closer and closer to it. And if we zoom out, we see that really happening. We are heading in towards this line, but we don't actually get there. We just keep going up or keep going down. And up here, the curve is getting closer and closer to 1, but it's never actually going to make it there. On the other hand, what we see is if we look left and right, we are flattening out as we go to the right and as we go to the left. And that's the horizontal asymptote. It's this line that as you go left and right, you're getting closer and closer to it, but you're never quite making it. And if we're looking at this, we are making it to 2 and we're heading down, and the line we're getting close to is y equals 1. And so as we move out, we're getting close to the line 1. And if we head out the other direction to the left, this part is moving up, getting closer and closer to 1. So that's the horizontal asymptote. And that is a little, it's less clear where this comes from by just looking at the equation. We'll talk about that, but it's not like you set up an equation so it's not like for this x equals 1, it's what makes the bottom 0. Where this 1 comes from, we'll have to talk about a little bit more. Any questions so far? Or any of the parts of these problems I've been explaining that you'd like me to go over again? I don't have the facial reactions, which makes it a little more difficult, but do let me know if you have any questions. This review part is all for you, making sure that you feel comfortable with a lot of these topics. A topic which doesn't get as much exposure in pre-calculus is the range. This word shows up, but it doesn't appear in as many problems as the domain does. And a part of that is because it's harder to tell from the equation what the range looks like. But from the graph, it's more doable. So the range is what y values occur. So here, what we can think is if we move in the y, the vertical direction, which y's can you go over and find a point on the graph with that y? So 2 is in the range because this point has a y coordinate of 2, 4, 6, and 8. And since this graph keeps going up, all of the y's, if we keep going up, those are all in the range. Similarly, 0 is in the range because -4, or sorry, here at negative, for x equals -4, that has height 0. There's a point with height -2, with -4, -6. So if we keep going down, all of those y values get used by a point on the graph. But what we can notice is there's no point that has height 1 on the graph, because this part is always below height 1. It keeps getting closer, and so every point just a little below 1 is going to occur as a height on the graph, but 1 isn't. And the same thing over here. This part of the graph keeps getting smaller and smaller, closer and closer to 1. So if you're a height a little bigger than 1, if you go far enough out on the graph, you're going to be the height of some point on the graph, but 1 isn't. So what we can see here is that in this case, this horizontal asymptote, that height isn't in the range because the bottom part never makes it up there, the top part never makes it down there. So 1 never actually, there's nothing you can put into this function which will have you output 1. And so y not equal to 1, or as an interval notation, it's the same thing we had here, but it's talking about which y's come out. The next two problems, zeros and y-intercept, these are really asking you, or if you know what points to look for, it's all about just identifying points. Zeros are which x's can you put in to give you 0. So what that's really looking for is which x's put you on this axis here. And -4 is the only one. This is the x where the graph crosses the x-axis. So, and that can be verified by looking at the formula here. If you put in -4 to this formula, you get 0 divided by -5, and that's 0. And if you set this equation equal to 0 and solve that, what you can figure out is that -4 is actually the only one. That's the only place where this graph crosses the x-axis. So a lot of these questions about the graph, what is a good way to really test that a lot of these different ideas fit together in the right way is either do them algebraically and then look at the graph and see that the answer you got matches up with what the graph looks like. Or what we can do is say, well, graphically we can see there's 1, 0, -4. What would I have to do to justify that by doing algebra? And so the graph tells you that you should only get 1, 0, and it should be -4. And if you solve the equation, x + 4 over x - 1 = 0, that will verify what you saw by looking at the graph. Right, the y-intercept, this is where it crosses the vertical axis. This is a total accident. There's no reason for this coincidence. It's also -4. It just happens to be that it's -4. -4 is the 0 in the y-intercept. Don't read anything into that. Sometimes coincidences happen. The last two parts here, where is it positive and negative, and where is it increasing and decreasing? Positive and negative, so both of these looking at the graph are not too hard to see what the answers are. So positive is, where is this graph above the x-axis? Well, this whole branch here is above the x-axis, so we want all of that. Also, here to the left of -4, we're also above the x-axis. But from -4, which is where our function is 0, over to 1, which is where we have this asymptote, the graph is below the x-axis. So looking at this picture, we can see we're negative in this middle part, going from -4 up to 1, and we're positive to the left of -4 and to the right of 1. And then writing that down as an interval says we're positive from -∞ to -4, union 1 to infinity, which is exactly left of -4, right of 1, and we're negative on that middle part, which is -4 to 1, from the 0 up to the asymptote. The last part here, increasing and decreasing. Increasing is, where's your graph going up as you move to the right, and where is it going down as you move to the right? That's a little, so before we come back to this one, we don't really need that. We put in x squared here. So here we are decreasing to the left of 0 because the graph is moving down as we move right from 0 to infinity. So to the right of 0, this graph is increasing because it's moving up as you move right. So that's what increasing, decreasing looks like. I guess also, you know what the words increasing and decreasing mean going up and going down in normal English, but we mean as you move right when we're talking about it for a function. And what's kind of weird about this graph is it's always decreasing. So as we're moving right, we're getting lower. We're kind of flat here, but we are moving down. And then we're getting lower, and then we're getting lower much faster as we get close to the asymptote. But then also, the asymptote here sort of breaks everything, and we restart on the other side. But on this other side, we're going down again. We're decreasing really steeply as we're close to the asymptote, and then we make it around this curve, and we're decreasing much more slowly, but we're still going down. So in this case, we're actually decreasing everywhere. So we're decreasing on the whole interval. What you could also say is minus infinity to 1, and then 1 to infinity. Here, this would also be an acceptable answer because this is really saying, one, there's an asymptote, and there our function isn't defined at all. It's kind of a weird point, so we won't say anything about it. We'll just skip over it. But if you look at either half, it's going down. Okay. Questions about this problem or any of the problems I've talked about? Or if there are some requests for other ones of these problems that you'd like me to talk about in the rest of our time. So some of the other ones are solving equations. There's a bunch of different examples of those. Some inequalities. A few of the more complicated ones make us set up these number lines, which you've encountered before, but is a sort of thing that it's always good to get a reminder. And then there's some trig at the end, which is also the sort of thing that brushing up on that is a good idea. And what was at the beginning before those kind of graphing ones? Lines, hopefully those are pretty familiar. And also, just to point this out, already in class, the sort of motivating problem is find the equation of the line. So knowing these ideas, and they're not especially complicated, and slope and equations of lines have been in the algebra classes we've taken for a while, but they are things that I'll just be talking about and not spend a lot of time explaining exactly how they work. I'll just kind of use them. What's up here? Oh yeah, and the first part was some algebra, factoring and simplifying. Any thoughts on what else you guys would like to see? My vote is maybe one of the harder inequalities. So we can do that. So let me try this. So what are some ways that I can make you do something? I feel like there was a way to do a kind of thumbs up thing in here. Or if you click on, I think, participants, a list of people in here shows up, and you can click yes or no. Oh, okay, so it's yes, no, faster, slower, and then like, dislike, and applause. That would be weird if someone gave me an applause one. But how about, what would you say, or would you like me to go over, say, problem 23 here? So do actually click on the participants and give me a yes or no. Okay, there's one yes. Okay, a few of them. Okay, a bunch of yeses. So let's do that. Okay. So solving this inequality, one thing that you can do, especially as you're doing this on your own, is, well, let's see this. So the first step is, sorry, I'm trying to think about what the best way to explain this is. Okay. As a comparison of an easy inequality or an easier inequality, if you don't have any powers of x, so in 22 here, it's 4x minus 6 is greater than or equal to 1. Here, you can treat it like an equation and move things to the right side to get x by itself. So here, if you add 6 to both sides, the inequality stays like it is, and you get 4x is greater than or equal to 7. Then you can divide by this 4 and gets you x is greater than or equal to 7/4. So these linear inequalities, these inequalities that don't have higher powers of x, you can treat like an equation. The wrinkle that you have to watch out for is if you multiply or divide by a negative number, the inequality changes direction. Where things get more complicated is if you're dealing with inequalities that have higher powers of x. So here we have an x squared. And the next problem, which is in a lot of ways similar, you have divided by an x here. So here it's not just enough to try to get x by itself. How we can proceed is first get this inequality so one side is 0. You could move the things on the left to the right. Here, it's a little easier to add 3 to both sides to get x squared minus 4x plus 3 is positive, is greater than 0. And then what you'll do with this is change it to an equation and solve that equation. This quadratic factors nicely. You're looking for things that multiply to be 3 and add up to be -4. There's not a lot of options for multiplying to be 3. It's 1 and 3 or -1 and -3, and the negative option works. So we have this factored form. This breaks into two equations, x minus 3 is 0 and x minus 1 is 0, and then you get two solutions, 3 and 1. What you do with those points for these more complicated inequalities is you use those to actually set up a number line. So 1 and 3 cut up our number line in these 2 points, cut it up into 3 pieces. And then here's the idea. 1 and 3 are the places where this function is 0. That's what we did. That's what we learned by solving this equation. So between here, meaning, or in the intervals that we're left with, meaning between, to the right, or to the left, this function, or this x squared minus 4x plus 3, has to be always positive or always negative. That's because if it was both, it would have to be 0 somewhere where it flips from positive to negative or negative to positive, but the only time it can do that is 1 and 3. So these are the only places where it can change. The way we use that is that if you knew, for instance, that our function was negative over here at one point, it would have to be negative at all of these points, because the only way that it could change to be positive would be moving across this point. If you're negative here, you can be 0 at 3, and then you have the option of changing to be positive or negative. So the way that we can use this observation is that if we pick points, so pick a point here, and I said below this is 0, a point here, 2, and over here, 5. You could pick any points in these intervals. So 2.5, 1.2. Over here it could be 5, 10, a million, whatever. Here, 0, -6, any option. Just pick any point in, for each of these intervals, pick any point. And then see, is this function, this x squared minus 4x plus 3, is it positive and negative at these test points? And so if you put 0 into this, you get 0 squared minus 4 times 0 plus 3, you get 3, that's positive. And what that means is, since this function is positive at one point in this left interval here, it's positive at all of those points. And you can also check if you put in 2, this function's negative. And so since it's negative at one point in this middle interval, it's negative at all the points in the interval. And lastly, if you test 5, it's positive, which means it's positive on this whole right side. So the way we can represent this, we don't need those numbers anymore, is we don't really care what numbers we got when we put in 0, 2, or 5, or whatever your test points are. All we care is, did we get positive or negative numbers? So what we can say is, we know that we were positive on these outer parts and negative on the middle part. And so we look back and say, this inequality we wanted to start with was the same or equivalent to this inequality. So we want to know where a function was positive. And this number line tells us exactly that. We're positive to the left of 1, which is this branch of our interval, and to the right of 3, which is this branch. What can also be helpful, and this is the last thing that I'll say, is when you're doing these, you can also go look at the graph. So the graph for x squared minus 4x plus 3 is a parabola, and this is exactly what we found. 1 and 3 are the zeros, we're negative in the middle, and we're positive on the outsides. So there's a lot more to look at. I, again, recommend taking a look through this and seeing what topics you might need to study some more. But all these kinds of questions are going to appear as parts of calculus problems. And so what you really don't want to do is you don't want problems to be difficult because of the algebra or because of the pre-calculus, because the calculus parts are already hard enough. And you don't want the pre-calculus steps to be bogging you down. You want those to mostly be fine so you can focus on the new stuff that we'll be introducing. Okay. So what do I want to say? So this review and this solutions version is posted on Canvas. If you have any questions, I can stick around for a little bit. Or actually, I have office hours after this, so you can have as much time as you want. But other than that, hopefully this was helpful and helps you figure out what, if any, review of pre-calc you need to do. And I will see you guys tomorrow.
Thank you.
Yeah.